This tutorial focuses on an important quality step prior to the classification and differential expression of the analysis. The delta-CT normalization standardizes the differences in nucleic starting material in our samples, something that is essential for comparing our biological groups. To do that, we normalize our data using a set of endogenous controls that maintain their expression levels despite different experimental conditions. Here are the reports we get after click-and-go execution. The first step in the normalization process is to check how healthy our endogenous controls are, as the expression level of an endogenous control is not theoretically meant to be affected by the samples we are analyzing or by different experimental conditions. Therefore, we are expecting to see plain profiles with a low overall variability, as we can see in this case. On the contrary, this detector is not what is expected of a control detector. We will see later that automatic selection methods will never choose it, and in case we select it manually, the application will notify us from the project panel alarms. This is the last case we want to highlight where some missing values have been detected. StatMiner quality control restrictions will not allow us to use this endogenous control to normalize our data. It won't be evaluated by any automatic selection method, and neither will it be available for manual selection. StatMiner is able to determine which is the best set of endogenous controls to normalize our data. But before we allow the application to do that, we should use this visualization to make a decision as to what we think might be the best control for our data. What happens if no endogenous control has been defined? Unless all the detectors in the data, target and endogenous, have been defined in the input files, StatMiner will consider all detectors as targets. So how do we define our controls? The application provides a tool which we can use to define the detector's role, new candidates for controls, or even discard some of them. Endogenous Controls Manager can be opened in the normalization step, or alternatively using the Tools menu. This tool contains an easy search functionality specifying detector name or task and the full list of detectors where we can reassign the task of any detector. In this case, we are aware of a certain target that would be good to be included as an endogenous control candidate. The search tool allows us to find it easily, and we only need to switch it to endogenous. By the way, this is the endogenous control we mentioned previously that has the missing values, but there is no need to reassign it as target, as it will be automatically ignored. In a similar fashion, all the target detectors with missing values cannot be switched over to endogenous control candidate. Okay, so we're done. This is our final set of candidates when we're now ready to let StatMiner determine the most stable set of endogenous controls. To do that, we can choose amongst any of the 3 scoring methods available in StatMiner for this purpose. As a whole view, this algorithm evaluates the variability of the expression profiles within each biological group as well as the variability between groups. The point is not only to test the stability of endogenous controls independently, but also to take into account the fact that groups of multiple endogenous controls are considered to be more accurate than normalizing data with just one endogenous control. As we will see later, if there is a combination of controls that is considered to be the most stable, the data will be aggregated to create a virtual endogenous control with which to normalize our data. We recommend that you check the user manual to get further information on these scoring methods. Although the application provides us with a full interpretation to advise us on different scoring method choices, for example, variation, stability score, etc., StatMiner analyzes those reports automatically, selecting the scoring method decision in the selection box with final candidates for the normalization. It is not mandatory to have a full consensus amongst the algorithms, but we can see here that the selection methods are actually quite similar. That means in our analysis, we can rely on any of the scoring methods to choose these endogenous controls. In this example, the consensus seems to be on these 2 endogenous controls. Let's see what these are and how they've been combined to create virtual endogenous control. This chart shows how the endogenous control candidates are colored based on the final role they'll take in the normalization process. These have been discarded by the scoring method as they were identified as having high variability. These are the most stable controls, and finally, this is the brand new virtual candidate selected as an aggregation of the selected controls. And here are the aggregation methods we can use to create our new virtual control. Okay, we're now ready to normalize the CT data, but first it is important to highlight that it is not mandatory to rely on any of these scoring methods to normalize the data. If we already know what controls to use, we can very easily make our own selection, and there is another interesting alternative to using our own set of endogenous controls, and that is the global expression level normalization. The global normalization is recommended when our dataset doesn't contain any detector that can act as an endogenous control. Global normalization creates a virtual control by taking into account all the detectors in our analysis, including targets as well as endogenous controls if they exist in the dataset. As a note, not all detectors are included in this process. Any detector with a missing value will be discarded as a potential control. Similarly, any detector with low expression level will also not be included in the generation of the virtual endogenous control either. However, it doesn't mean that they won't be normalized and included in the next step of the analysis. Okay, let's go back to our sample. These are our most stable endogenous controls, and what we are going to do to get delta CT values is to calculate the differences between this profile and each sample CT value. In order to better understand this process, we can inspect the distribution of our CT values of each sample and our virtual endogenous profile as well. Delta CT computation will subtract each normalization factor of our virtual control from the corresponding set of sample CT values. So okay, we are now ready to go. With this option, we are telling the application that we also want to normalize our endogenous control so that they can be available in the final analysis steps. These are the new detector profiles after the normalization process, but it is best to inspect the results by comparing the box plot distribution before and after delta CT computation. This is the distribution of CT values before the normalizing of our data, and this is how they've been refactored after subtracting the virtual profile sample by sample. Differences in the starting nuclear material have now been standardized. We will finish this tutorial by mentioning that the project panel is recording all the settings that we are using in the analysis, such as selecting the scoring method, endogenous control selection, etc., as well as some quality warnings that might appear during the normalization process. In this case, the scoring method did not select this control to normalize the data, but the project panel will always notify an endogenous control with very low expression levels, as in this instance. Another warning that may appear, although not in this example, is the quality of our endogenous control. StatMiner automatically processes the stability of multiple random combination of targets to determine whether this random selection is better than the specified endogenous control. If so, that it is recommended to use the global expression normalization rather than an endogenous control combination. Okay, so now our data has been normalized and we are ready to continue with the last step of the analysis, clustering and differential expression analysis.